Okay, we're now going to go over the Unit 9 study guide. Okay, so the first question is convert 3.11 kPa to ATM. Okay, so I'm going to do this both in two ways, because originally I showed you guys how to do it with the picket fence, and then if you're in Mr. Mefford's class, I showed you how to do it with just dimensional analysis with units canceling. So I'm going to show you how to do both on this one. So the first thing we're going to do, let's do the picket fence first. So 3.11.8 kPa. Now you're going to need the notes with the pressure conversions, because you're going to have to know which two units we're using. So the first one, we need to do 1.0 or 101.3 kPa and then 1.00 ATMs. So those are the two units we're using. So we're going to take 3.11 times 1.00 divided by 101.3 kPa gives you 3.08 ATM. Now, if you're doing it with the units canceling version, you're going to do 3.11.8 kPa over 1 times, and then you're still going to need your two units that we're using, 101.3 kPa and 1.00 ATM. And this cancels. And then once again, it's 311.8 times, here, I'll write it out, times 1.00 divided by 101.3 equals 3.08 ATM. Okay, so that's your answer, 3.08 ATM. Okay, so let's go on to the next one. Okay, for this one, we're doing 897 millimeters of mercury to ATM. So, of course, the first time we're going to use the picket fence. So 897 mmHg. Our conversion factor uses 760 mmHg to 1.00 ATM, which is 897 times 1.00 divided by 760. So our answer is 1.18 ATM. Now we'll go by way of the units conversion that Mr. Mefford does. So 897 times 00 ATM. So you're still showing your units canceling, and you still get 1.18 ATM. Okay? So 10.5 PSI, 14.7 PSI, 1.00 ATM, and it's 10.5 times 1 divided by 14.7, and we get 0.714 ATM. Now, if we do it the other way, 10.5 PSI divided by 1. It goes on bottom because we're trying to get the PSIs to cancel. 0.714 ATM. Okay, we're going to convert 2.17 ATM to kPa. So we're going to use our picket fence first. So 2.17 ATM and 1.00 ATM goes on bottom, and 101.3 kPa. So this is 2.17 times 101.3 divided by 1, and that gives me 220 kPa for my answer. 1 Once again, you still need the same conversion factor, which is 101.3. Come on, let's do this right. 0.3 kPa over 1.00 ATM. That way your ATMs cancel, and you get 220 kPa. Okay, so this time let's convert 683 millimeters of mercury to kPa. So we're going to take 683 millimeters of mercury. Now, we're going to be doing millimeters of mercury, so I'm going to put those on bottom, and kPa. So this time we're going to do 683 times 101.3 divided by, 760. And when we do that, we get 91.0 kPa. 683 millimeters of mercury. So use whatever method is best for you. If you like the unit conversion like on bottom, you don't want to use the picket fence, you don't have to use the picket fence. As long as you can figure out how to do this, which one goes where, you should be good. Remember, always the one you have on bottom, or the one you put on bottom is what you're given, and then the one on top is what you're looking for. Okay, so our answer, either way you do it, is 91.0 kPa. Oops. Now this last one, 39.7 psi to kPa, I'm not going to show you the unit conversion one. I'm just going to do the picket fence, but you can use whichever unit or whichever method you like best. Okay, so this one's 39.7 psi, 14.7 psi, 101.3 kPa. And that's going to be 39.7 times 101.3 divided by 14.7. And when I do this, I get 274 kPa. Okay, so those are all the pressure conversion problems. On the test, I can tell you right now, there's at least one where you're going to have to do a pressure conversion in the middle of the problem. Okay, when that pops up, I'll give you a little hint saying, make sure both pressure units are the same. When you see that, you have to convert. Now, it won't matter which one you convert to, but as long as both pressure units are the same. So you will have to do one pressure conversion in the middle of the problem. Okay, let's go on to the next one. Okay, so number 3. A 3.18 milliliter sample of a gas is at 806 millimeters of mercury. If the pressure is lowered to standard pressure, what's the new volume? So let's figure out what we've got here. We've got a volume, and we got a pressure, and then we have a second pressure. So that's a 1, and then we're looking for V2. So that's what we're looking for. Okay, so this is obviously a Boyle's law equation. It deals with V's and P's. So V1, P1 equals V2, P2. Now you can right now plug and chug, plug the numbers in and chug out the answer as is, or you can rearrange the variables first and then do the answer. I like to rearrange the variables first. So if I'm looking for V2, I'm going to put the P2 over here. So it's V1, P1 over P2. Okay, so V2 equals, so 31.8 milliliters. And I'm going to put my units in here just because I want to make sure my units cancel and what I'm getting out is what I'm supposed to have. So 806 millimeters of mercury. Now, standard pressure. I have millimeters of mercury, so I'm not going to put 1.00 ATM because I didn't start out with ATM. So my standard pressure in millimeters of mercury is 760 millimeters of mercury. So that way my millimeters and mercury cancel, and I'm left with milliliters. So 3.18 times 806 divided by 760 is 33.7 milliliters. And that is my V2. And milliliters is a volume, so I know I did it right. Okay, so a sample of gas has a volume of 0.515 liters. So there's our volume. If the volume is decreased to 223 milliliters, so we have our V2, so we're going to put a V1 there, the pressure is 0.819 ATMs. So there's our P2, and it's looking for P1. Okay, so this one we are doing P1 equals. So if you do the V1, P1 equals V2, P2, we're solving for P1. So we're going to put that over there. So P1 equals V2, P2 divided by V1. So P1 equals. Now we need to have our two volumes exactly the same. So I'm going to start out with the milliliters and then times it by 0.819 ATM. Now we have to convert the liters to milliliters, or you can convert the milliliters to liters. Either way, it doesn't matter. But if you convert liters to milliliters, liters times 1,000 equals your milliliters. So it's 515 milliliters. That way our milliliters cancel, and we get 0.356 ATMs. Okay? Okay, so number 5, a 121 milliliter sample of helium gas is at 35 degrees Celsius. So we have a volume and a temperature. If the volume is increased to 200 milliliters, we have another volume. So I can go ahead and put the 1, and 2, and we're looking for T2. Okay, now the equation is V1 over T1 equals V2 over T2. So V1 is 121 milliliters. Our T1. Now I'm giving it to you in Celsius. It needs to be converted to Kelvin. Because remember the gas laws, you can never, ever, ever use Celsius. You have to use Kelvin. So degrees Celsius plus 273 equals Kelvin. So 35 plus 273 is 308 Kelvin. And then 200 milliliters divided by T2. So I'm going to go ahead and do the cross multiplication. So T2 equals 308 times 200 divided by 121 equals, now you're going to multiply that out and you're going to get 509 Kelvin. But I gave you the original temperature in degrees Celsius. So you need to convert that back, this Kelvin, back to Celsius. You do that by subtracting 273. So we get 236 degrees Celsius as our answer. Okay, pretty simple. Let's go on to the next one. Okay, a sample of gas is stored at standard temperature. So there's a T. If the temperature is increased to 20 degrees Celsius, so now I have a T2, so I'm going to go ahead and put that as a T1, the volume increases to 125 milliliters. I know that's V2 because it's connected. It's in the same sentence as the 20 degrees Celsius, which is our T2. Plus, it's also asking for the initial temperature, which is V1. So we're going to use the equation V1 over T1 equals V2 over T2. Okay, our V1 is what we're looking for. Now our T2, we're not going to use 0 degrees Celsius. We're going to use 273 Kelvin. So remember, that's our standard temperature, it's 273 Kelvin. Our V2 is 125 milliliters. And then our T2 is 20 plus 273, which is 293 Kelvin. So at this point in time, we're going to have to do our little cross multiplication. So V1 equals 273 Kelvin times 125 milliliters divided by 293 Kelvin. Crosses the Kelvin out, so our answer should be in milliliters, which is what we want. And we get 116 milliliters. Okay, number 7. A sample of argon gas is stored at 10 degrees Celsius. Okay, so we have a temperature. If the temperature is lowered to negative 25 degrees Celsius, so we have a T2, the pressure becomes 1.01 atm. So we have a P2, and it's asking for a P1. Okay, so this one is Gay-Lussac's law. It says P1 over T1 equals P2 over T2. Okay, so P1 is what we're looking for. T1, remember, once again, we need Kelvin. So 10 plus 273 is 283 Kelvin. P2 is 1.01 atm. And our T2 is negative 25. So 273 minus 273 minus 225 is 248 Kelvin. Okay? So this time we're going to be cross multiplying these. So P1 equals 1.01 atm times 283 Kelvin divided by 248 Kelvin. Kelvins cancel. So 283 times 1.01 divided by 248 is 1.15 atm. So really the whole idea here on all these gas laws, so that you know which law to use, you need to make sure that you're labeling or at least identifying what variables you've got. And that should tell you what variables you need, what variable you need, but it'll tell you what gas law to use. Okay, number 8. A sample of hydrogen gas is stored in a container under STP. Okay, right there we have a T and a P. So this gives us our T1 and our P1, or just T and P if it's the ideal gas law. So if the pressure is increased, so there's our P2, what is the new temperature, or what is the temperature? So that's our T2. So once again, we're using P1 over T1 equals P2 over T2. Okay, so P1, now it's giving it in kPa for P2. So I want to make sure I use kPa for my P1. So standard pressure in kPa is 101.3 kPa. T1 is 273 Kelvin. Remember, standard temperature is 273 Kelvin, not Celsius. Okay, our P2 is 205.4 kPa. And of course, we're looking for T2. So do our cross multiplication thing. So T2 equals 273 times 205.4 divided by 101.3. Oh yeah, if I put the units in, my kPa's would cancel, and then I'd be left with a Kelvin. I get 554 Kelvin. Now, because I did not ask you for the temperature in Celsius, you can leave it at Kelvin. But if this was a test, your multiple choice answers would probably be Celsius. So I'm going to go ahead and convert this to Celsius. So minus 273 gives you 281 degrees Celsius. Either answer is correct for the study guide part anyway. Okay, what size container will 36.05 grams of argon gas fit into at STP? So we have a volume, we have an N, we have a T and a P. So we are using the ideal gas law. PV equals nRT. Now, so P equals 1.00 ATM. I like using that one because I know the R value off the top of my head. So it's liters per ATM, moles, Kelvin. V is what we're looking for. N we have to convert to moles because we have mass. So 36.05 grams of argon. Look up argon on the periodic table. It's 39.95. So that gives me 9023 moles. And our temperature, of course, is 273 Kelvin. Now we need to solve for volume. So we're going to put the P underneath there. So now it's V equals nRT divided by P. I'm going to move this up a little bit. Okay, so volume equals N is 0.9023 times R, 0.0821 times T at 273 divided by 1.00. And when you do the math on this one, you get 20.2 liters. Okay, number 10. At what temperature, so we've got a T, is a 6.00 gram sample of argon gas if it takes up 1.54 liters at 1.0 ATMs? So this time I'm looking at the ideal gas law again. PV equals nRT. Okay, so let's define our variables. Our P is 1.02 ATM. Our volume is 1.54 liters. Our N is 6.00 grams divided by, remember we need moles, grams per mole. So we look up argon gas again, and this time we get 0.1502 moles. Our R is 0.0821 liters per ATM, mole Kelvin, and our T is what we're looking for. Okay, so I'm going to move this up a little bit. Now, since we're looking for T, we need to take this and put it underneath the P. So our equation actually is T, if I can get this to right, oops, sorry guys, I'm having some problems with the equipment. Okay, T equals PV over NR. Okay, so now let's go ahead and put the variables in there. So T equals 1.02 times V, which is 1.54. The point's not showing. There we go. N, which is 0.1502, and our R, 0.0821. Okay, so when we do the math, we're going to take 1.02 times 1.54. Now you can do this in one fell swoop on the calculator. So you take 1.02 times 1.54, then you divide it by 0.1502, hit the enter or the equal sign, and then do another division. So divide by 0.0821. When you do that, you get 127 Kelvin. Now remember, it asked for it in degrees Celsius. So I need to take 273 minus 273, and I get negative 146 degrees Celsius. Okay, hopefully that was easy enough for you. How much grams of laughing gas, N2O, is in a container that has a volume of 750 milliliters at 852 millimeters of mercury and 22 degrees Celsius? So we're looking for N. We have a volume, we have a pressure, and a temperature. Okay, so I'm not going to worry about doing P equals, T equals, N equals, V equals, and R equals, and T equals, and all that good stuff. But the equation we're using is PV equals nRT, but we need to solve it for N. So N equals PV over RT. So N equals, so our pressure is 852. Our volume, now we can't use milliliters. We have to use we have to use liters. So you take 750 divided by 1,000 and you get 0.750 liters. Our R value, we have millimeters of mercury. That means we have to use the 62.4. And then our T is 295 Kelvin. When we do that on our calculator, we're going to do 852 times 0.750 divided by 62.4 equals, then divided by 295. And we get 0.0347 moles. But we want molar mass, or we want grams. So we have to multiply it by the molar mass of N2O, which when you calculate it, it's two N's plus an O, is 44.02 grams per mole. So our final answer is 1.53 grams of N2O. Okay? Okay, last one. Number 12, a 15.7 gram sample of helium gas is stored in a 25-liter container at standard temperature. What is the pressure in ATMs? So we need to use the, once again, you're looking for, you have all the variables for PV equals nRT. Now, we're actually going to solve for P, so we're going to put the V underneath there. So P equals nRT divided by V. So P. Now our N, we've got to convert, so let's do that first. N equals 15.7 grams, and it's helium. So we're going to divide it by 4.00 grams per mole. And this time we get 3.925 moles. Okay, so our N is 3.925. Our R value, because it's an ATM, we're going to use the 0.0821 liters per ATM. We're not going to put all the units down right now. And then our temperature is standard temperature, so that's 273. And our volume is 25. Okay, so when we do that, multiply it all out, we get 3.52 ATM. Okay, so that's pretty much it for the review. Hopefully this helped. If not, you can get a hold of me by email or however, and maybe I can explain some more. But hopefully this helped you work it out. This is pretty much a good example of the types of questions that are going to be on the test. Okay, so have a good day. Bye.